All right, let me erase this, and now let's start with your question about dynamics. What is the dynamics? How we see this? What is the polymer model? So this is part one. This is polymer dynamics. So all what I'm discussing here is based on classical polymer models, but the analysis is the new part. How we analyze them compared to the steady state analysis is present in all very good classical books, like Doye-Edwards. I mean, there are infinite number of very beautiful books about this. Doye-Edwards, there is about polymer model. I think it's 80 something, 84 or 85. There's a book of Rubinstein about polymer model, and there are many very interesting books. So let's start with the Rouse model. The Rouse model is beads connected by spring. So you have an energy. So let's call R1 Rn the position of the bead. It can be time dependent. We're in dimension 3, so this is a vector or point in dimension 3. And so now we need an equation for equation of motion. So we took the Smoluchowski, I mean the classical version is the Smoluchowski limit of the Langevin equation. So you have just a motion, an equation for the derivative of the position, which is the velocity, which is minus the gradient with respect to Rk of the potential, which I'm going to write in a second, plus noise, square root of 2d. Let's suppose d is, you can attribute whatever you want. So let's suppose d is a diffusion constant for this bead, which is constant along your polymer, plus your Brownian noise. And the U of R, which is the energy, is U of R1 Rn equals kappa divided by 2. So this is the same kappa that we've used over there. This is just a spring constant. Sum of Rk minus Rk minus 1 squared, and k has to go, let's say, from 1 or 2 to n. All right, so for example, if you have if you look at the monomer, let's ignore the two end ones, because this guy, they don't have any more a guy here to connect. But if you're in the middle, basically you are connected to the two neighboring monomer, and the force is simply the spring constant that's bring back the monomer to a position. So for example, here, general equation is for monomer that are inside. This is 2Rk minus Rk minus 1 minus Rk plus 1 kappa plus noise. And so, for k from, let's say, 3 to n minus 1, the extreme part, or 2. The extreme part are different. One term is out. And so last week, Kevin made a comment that this is really like a Laplacian operator, discretization of the Laplace operator in that one dimension. And this is important for understanding what can be done with this polymer to create a polymer a little bit more complicated. So this is Rouse. It has interesting properties. You can look at okay, let me remind you some of the basic property, and then from here, from So basically what we're going to do is you can find a base that will diagonalize this matrix. And we'll see it makes sense to diagonalize. And with this diagonalization, we're going to construct a polymer. Will have a predicted, a fixed alpha exponent. Okay, so some properties. Again, this is very classical, but so Rn in steady state minus the position, R1 minus Rn, for long time asymptotic, so you can look at it at infinity, is basically the mean, when you average over realization, it's of the order of n b squared. So I haven't said this, but the mean position, so b here, it was b is the mean position between R1, Rk, any of them, Rk minus 1. Suppose this is fixed. This is the second order properties. All right, and also an important quantity to characterize the polymer is called the radius of gyration. Radius of gyration, basically, gyration. Basically, we have a polymer, and by symmetry, you would like to ask what is the radius where this polymer is confined, and the radius of this is called the radius of gyration, Rg. And Rg for a polymer, so it's defined as you take the sum of the position Rk, you take the mean position, let's call R mean. R mean is the average over R1, Rn. You take its square, you take the ensemble of this, and this behaves basically as a square root of n. And there is a constant here, and the constant, so it's b divided by square root 6.
Is b the square root of what you wrote up?
No, b is...
What you've defined as b?
b is here. Yeah, b is square root of this, sorry. Okay, so now let's go into the study of this. Not that it's technically difficult, but this is the frame we need to construct the other polymer. So let's diagonalize this. So I'll give you basically the matrix that we need. So let's define UP, which is the sum of alpha Pn, and with sum over n from 1, I think, to n or n minus 1. It's not written in my note. So alpha P1 multiplied by Rn. Yeah, you sum over all of these. And let's take alpha Pn, which is the matrix, which is 1 divided by square root of n, if p different if equals 0. Otherwise, we'll take 2n square root cosine n minus 1/2 p2 divided, so 2p divided by capital N. So using this transformation, you can write the an equation for UP. So you differentiate this with respect to time, du dt. So this is independent of time. So this is the Rn dt. And Rn dt, this is given by this. So I'll skip some steps. Basically this, diagonalizing this, so you are going to end up here with a single term. And I'm going to write an ensemble of Ornstein-Uhlenbeck processes, which is du dt of UP. It's minus d kappa p UP plus square root of 2d w dot tilde. So let me explain. This is the Ornstein-Uhlenbeck Uhlenbeck process. D is the diffusion coefficient. Kappa P, this is the interesting quantity, which is 4 kappa. Kappa is a spring constant defined here. So 4k sine p pi divided by 2n squared.
These are the eigenvalues of that.
Yes, this is the eigenvalues of this. So you have this diagonalization. In here, what usually you have is, because of the sum, you are going to sum noise. But if you sum all of this noise, of these noises, this is like a single Brownian noise, and this you can see that it doesn't affect, the coefficient is exactly 1. So you just call this as a new noise, and this is what you get. So this is much simpler to study. From this you can calculate immediately, for example, the mean, the second order moment of UP, then plug, so you have this matrix basically is orthogonal, so you can basically Rn is the same alpha Pn as a function of UP, so you can get all the property you want. So this is important when we are going to calculate the second order properties. And so let me so this is true for P equals, it's not written here, but 1 to n minus 1. There is U0, because we have n beads, so from 1 to n. This is n minus 1, but U0 is like the motion of the center of mass. That is, you have your entire polymer that moves. So U0 is just the motion. U0 is just the motion of the center of mass. That's why, if we're interested in looping, for example, we don't care about U0. All right, so maybe I'll go.
What you've done is you've diagonalized the
Yeah.
into a set of Ornstein-Uhlenbeck.
That's right. That's right. I mean, this is the classical. I haven't done anything right now. This is classical. Now, let's discuss. Okay, let me introduce at this moment. I'll come back to here later. Let's discuss what you can do with this. Suppose instead of 2, I call it beta. I change 2 by beta. If you go back, so this is a reversible process. If I have 2, you can go back in here. And now what happened, so in the Fourier space, you do your transformation, you change a coefficient, and now you want to see what happened when you go back. You have modified here, basically, your eigenfunction. Now, before this, the eigenvalue. Before, the eigenvalue was such that everything was cancelling, such that you had only interactions between the neighbors. Now, because if you change the beta here, I mean, you change 2 by beta, you want to see how it propagates. All right, let's do this. And then let's calculate for when we are going to change here, let's calculate the mean square displacement of one of the monomer and compare the situation when we have 2 and when we have beta. And now, what I would like to show, I'll write this and then we'll make a 5 or 10 minutes break. We are going to see how the alpha, anomalous exponent, are going to depend on this beta. So right, this is where we were last week, more or less. So let's do this.
So couldn't you do this quickly with spectral calculus?
I don't know, maybe, what do you have in mind?
I mean, essentially, just you're taking all the eigenvalues and you're raising them to the beta halves power, right? Then presumably that means you've just taken the operator in your equations and changed it to the beta halves power of that.
Mm-hmm.
And then go from there.
Okay, but what I'm going to show you here is that now we have a procedure of calculating, implemented it in a computer manner, I mean calculable, when you want to calculate things, that we are going to be able to have explicitly, because we work in this Fourier space, the long-range connections. So we cannot do the calculation. We cannot run a polymer, a beta polymer. We make this long-range connection, and it will have alpha as anomalous exponent. So we have an algorithm procedure. Can I do that with what you said?
No, I think this was what Kevin was talking about last week, where you can just think about.
You could do it, but I'm not sure. I'm thinking this would be more insightful. But you could do it. Yeah.
This is a construction procedure.
Do a spectrum.
So I mean, if while I'm writing all of this, you have an idea to simplify it, this is very interesting. I mean,
it's nothing more than what Kevin said last week. So.
Okay, all right. Okay, so now the idea of doing this is now it's a constructive procedure. All right, so let's so the potential, the U, I'll just erase it. Okay, so let's call it UR1, or the potential, which was R1 or Rn. It can be also written as the potential of U1, Un minus 1, and this is exactly one half of K tilde P. So K tilde P is Kp, where I change 2 by beta. UP squared. So this before, let me remind you what it was. It was a 1/2 kappa sum of Rk minus Rk minus 1. So here I'm skipping one step. The step is to write or change Rk by the expression in terms of, so yeah, maybe I should write this down. So you can invert the equation. So let me write this somewhere. C is any of the monomer. This is P equals 0 to n minus 1, alpha Cp Up. So this is basically, we wrote U as a function of R, and this is now R as a function of U. This is just to invert it. So if we replace this in this formula, you get this sum of squared here. All right, so now let's go back. Suppose, so this we did with factor 2. Now you take the same formula, and now you put here the kappa p, which is sine to power beta of what is written there, which is 4 kappa pi p divided by n of 2n. All right. So when we have squared, everything is going to be beautifully like this. Many cancellations. Now, in general, what you get from here is we get 1/2 of the sum of kappa p, and then we just replace by this formula, which is the sum of alpha pn, and this is what I meant by explicit way to calculate the different forces. So this is squared, and now you can expand this sum. It's nothing very creative, and you reorganize it, and you can always write it as the sum of RL, Rm, ALM. And now for this ALM, this is the matrix, which is the sum of 1 over n minus 1, kappa tilde p, alpha PL, alpha MP. So just to show you what you get 4 kappa. There is 2, so this is 8 divided by n, sum from 1 to n minus 1 of sine beta p pi divided by 2n, cosine of p minus 1/2 p pi divided by n, and it has to be symmetric, so I have to multiply here. It's not great, right? So I multiply here, this is multiplication, by the same term. Sorry, this is sum over L, so there is an L here, and I have to have an M here. So this is cosine of the same term, so this is M minus 1/2 of P pi divided by N. So believe me, when you have squared, you have all cancellations. When you have a general term, you have no cancellation. So this will give you the information, so you can always rewrite this potential. So let's call it psi as 1/2 of the sum of Aij Ri Rj, which is not the connections. This is A here is the connection between any monomers. You fix I and you have all the J's. So now you can expand this so that it is equal to this, and you get the information about your Aij, from which you can now run a simulation. A simulation. Now, let's break here. After the break, we'll show the property, which is the interesting property, is that, so after the break, I would like to show, so that I make sure that you're coming back. Yeah, I think I lost it. Okay, I have to. So what I want to show after the break is that if you take not the end one, but telomeres in the middle, monomers in the middle, the mean square displacement. So T0 is fixed. Let's take 0. Take this squared. When T is small, these behave like a constant. And T to the power, I think it's 1 minus 1. -1 divided by beta. For T small, A is a constant, and the beta here is the same. So we're interested in when this quantity is positive and it's going to be less than 1. Basically, what this says, the conclusion I'm giving the conclusion before we have proved this. The reason, I mean, it's not only reason, a possibility, or when you extract an anomalous exponent from a tagged monomer, this says that it is contained. You can have, let's say, between 0 and 0.5. If you have a prescribed alpha, that is, if you look at your measurement and you get 0.4, for example. All right, you invert this formula, you find beta, you can do the construction, you get this long range. So I haven't shown to you, but the long range connections are decaying very quickly. Basically, you connect the two, but all of them have to be connected, but that's very small. But it's very important. You need this connection, even if it is small, so that this is prescribed. And so the one possible interpretation, I mean, is that the anomalous exponent comes from the properties of the chromatin. it has nothing to do with the local interaction, which is a question that is under debate. What is the why you have an anomalous exponent? And there is more. For example, for the same chromatin, depending where you are, the same chromatin, the same point that is labeled, you find different alpha. Why? A possible interpretation is that the chromatin contains different type of molecule, different type of binders. But at least from the analysis of the polymer, we can say we are able to construct a polymer, given polymer, with a prescribed exponent. Right? So I'll show that when we come back. And also, I want to do this, and I want to do the mean looping time. How long it takes for a Rouse polymer. So we did also the looping for a beta polymer. That is, what happens when you have all this connection, you take the endpoint, how this will affect the mean time it takes to loop. And actually, it affects, because instead of having the power 3/2, which was written before, it's now a power that depends on beta. All right, so I want to do this, and how long it takes for when we have a Rouse polymer for the two endpoints to meet and to recover the formula that we had on the board, and what is the method? Because the method is very different from all the methods we have developed, either us or Michael Ward of the group at University of British Columbia. It's not based on match asymptotics, Green's function. It involves a theorem that was developed about 20, 30 years ago. When you have a space and you remove an ensemble, what is the time it takes for a Brownian motion to remove an ensemble in very high dimensional space? And basically people looked at this by saying, what is the shift in the spectrum of the Laplacian? That is, you have a domain, you have some boundary conditions, you can calculate the spectrum of the Laplacian. Now suppose you remove a small domain. What is the consequence on the spectrum? So this is what they calculated. It has a shift in the spectrum, and the shift is exactly what you can use to connect with mean first passage time. So this was a completely different approach, and so I want to discuss this for the next hour, and if we don't have time to finish, I'll discuss this also for next class.
Very good. I thought word and color did precisely take a point of view of, you do some localized change, cut out part of their domain and look at the change in the spectrum, and that's how they got the mean first passage time results.
Oh, who did that?
Word and color, no?
Michael. Well, how they did it? How they did it? It's a good question. The 1993 paper in Science Journal of Applied Math, this is probably what you have in mind.
All I'm asking is, it sounded like you were saying something is different. It's
different, yes, it's different. They did in dimension 2, dimension 3, by a process which is match asymptotic. That is, you look at a solution near the target and you glue far away. Here it's going, for what we did for the polymer, it comes from a different vision where you have to remove something that has a structure. That is, it can be torus, it can be, it's basically the tubular neighborhood of n-2 or n-3 dimensional manifold that you are removing. This is very different. And their proof, one is probability proof, and the proof for Michael is gluing. You rescale everything in here, you find what is called an inner layer, that is some kind of how the solution behaves. And this is basically pushing everything at infinity, and then you have to connect with what's called an outer solution. And this is, you need for this what is called the solution of the Weber electrified disk problem, which is well known. You have an electrified disk, and you look at the potential far away. This is how this method is constructed. Nothing to do with this one. Okay, let's break, let's say 10 minutes. That's okay? 10 minutes, and then we will see how good, maybe I'll do only a half of what I said, and then I'll postpone it for next week, depending how you feel. Okay, next week, no class. I will say it, because once it happened that I forgot to say it, but next week, no class. And then the week after, we'll resume. Next week, no class.
That time some guy from Schlumberger showed up, right?
I'm sorry?
And that week, someone from Schlumberger showed up to sit in on your class, right?
I think, yeah, somebody showed up and he was very upset. So I wanted to make sure that, and then the director came. And, you know, you have to be there when you give a class, but I said it, and said that, I didn't say it for the announcement.
Yeah.
All right? Okay, let's break 10 minutes. All right. Okay, so we should start now, either by doing the looping or doing the construction of the beta polymer, of the mean square displacement.
Did you discuss whether the Rouse model is a good model of DNA to begin with?
I just got this question.
Yeah.
Yeah, so there's a debate, and there was a couple of publications showing from an experimental point of view that the alpha was quite good. The approximation of alpha is 0.4, 0.5,
This is
0.5.
for the anomalous diffusion.
Anomalous diffusion. So it came from this literature. The argument came from single particle trajectories and from the alpha, that it was quite a good description, although there are...
So the alpha you get from experiments is close to the alpha you get
the mean is close to 0.5, although for bacteria, the mean is 0.4. And there is a large variability. That's why we built all of this polymer model to try to account for this spectrum. So this is how we saw this construction of the polymer to go in that direction.
Well, I asked him this earlier, he gave a better answer. It's because it's on a big scale. All of these twist bend coupling and whatever, worm-like chain is apparently small scale, and he's on a big scale.
Larger scale like nucleosomes.
Right, but I mean, if you want to tie this down to actual distances in space and things like that, you have to say what D is and
Sure. Right now it's just about
qualitative features of the...
That's right, how things behave. For the connections, so now, I mean, the important question that you're raising is, now, what is the scale we are discussing?
Yeah, what's the scale?
Yeah, is it 1 megabase pair? I wanted to postpone this later. So actually, you can decide, you can choose. And so, for example, recently we looked at this chromosomal capture data, and one bead was representing 3 K-base pairs. And at this scale, this is a reasonable assumption. If you go smaller, you can go to all kind of problems, because the chromatin is not just like presented like this. It's much more complicated. You have the nucleosomes. You have this is a picture. This is a textbook's picture. I'm not sure this is correct. It is, but it has some of this. It goes twice around, goes continue, and this is probably folded. So there is more into this picture. But from the analysis at a order of hundreds of milliseconds and more.
Well, I would say you can probably fit the data by adjusting the parameters in the Rouse model too.
You can extract information.
The effective values of the parameters from.
But however, alpha is something that is more intrinsic. And when you get this alpha, basically you get some information about the statistical properties.
Yeah.
So you have to fix, for example, if you do a simulation, you say, let's fix this is what it represents, and then you work with this scale, saying that, of course, at lower scale, this is the physics is certainly completely different.
But okay, my other question is, what about the excluded volume for the problem? Because that you can't scale out just.
No, this is much harder. Okay. So this is the simplest of the model that account for some of the phenomenology of the data. Now, if you want to get closer and closer to reality, you have to account for Lennard-Jones exclusion. You can also have some bending properties and torsions. Yet, when you look at this and get the behavior, the asymptotic behavior here, it tells you a lot about, with this very rough model, about some statistical properties. And what we have observed from the statistics of the data, you still can account for a large fraction of them without putting all of this additional information that you suggested. Again, this is like we have a cutoff at 3 or 4 or 5 kb, kilobase pair. We don't care about what happened below the scale, and then we try to look at this long distances properties. Your question is actually important and very important in the following context. Now let's suppose you do UV damage. I'm okay with the. It works?
No.
No? What shall I do?
Which you told me.
Okay. Is it okay? What was it? Yes. So recently, we had the following data where you irradiate a cell with UV light. Now you create damages. And now became the new player came, which was the relocalization of the nucleosomes. That is, you have this structure. Imagine you have a bead here, which is, let's say, hundreds of base pair, of, let's say, 500s. And they start to move. And this is complicated because if we do that slowly, you have the DNA that will wrap, I don't know, 1 or 2.5 or 2.7, a certain number of them, and then it moves to the next one, and then move a certain number of, not a complete circle around. And this guy is starting to be relocalized. Now, this is a very touchy question because this model is not anymore valid. Now we have to account for this localization that they have found experimentally and try to address the question of how the DNA has changed its organization, where now we have this additional player. For example, what happened when 30 or 40% of these guys have moved? How do you model this? You cannot anymore use the classical Rouse. How do you model this? So if you go now to, there are models in the literature about looking at the interaction between this nucleosome and the entire chain. It is very complicated. The time scale, if you do a simulation with this, is very short, much shorter than minutes or tens of minutes that you want to achieve with your simulation to look at how things are redistributed. So basically you are stuck if you do simulations that account for all of this local interaction. So here, I have no answer for this. This is the construction. A sort of hybrid model should be constructed where you look at this nucleosome, how they are going to be redistributed, and let's take this Rouse polymer as a backbone of the structure. Now you have to couple the two in a coarse-grained manner so that you can run long-range simulations. So this is we're trying to look at this. This is this is an important point, and the motivation came from this UV light, where you can see beautifully that everything is extruded from this region, and then things start to come back. And then they looked at what is the fraction of nucleosome that went out, and are they going out of this region because of translocation on the DNA, or because they went outside and then they can float like diffusion? So that's okay. So there is no absolute model. A model depends on the questions. Here we're looking at long-range processes and also rare events such as looping. And we will use also this information, alpha, again, coarse-grained statistics that can be extracted from data that can now be related to the interaction in this coarse-grained polymer model. Again, there is a big debate in the literature about what is alpha, where it comes from, what it means. Here we propose that just following the step of the analysis, we give some interpretation. I'm not saying that, you know, it's true, but at least there is something. And we have this procedure of construction. Okay, so let's continue. From here, we have two options. I can show you the mean square displacement. I think I'll start with this. How it is calculated. It's a bit systematic, but at least I'll show you the steps. And the detail of all the calculation are in the papers, but at least I'll explain just the detail. I like calculation because this is my job. Mathematics for me is about how to calculate and how you see things happening in calculations. And then we will move on with the looping, how long it takes to loop and how you do this calculation with these different methods. Okay. And yes, and also there is, maybe this will be for next time, this how to extract Kevin answered the question about the force. How do you extract the force applied somewhere when you look at something at another position? Okay, so let's concentrate on the mean square displacement property of Rouse, and so I'll do it in general for beta polymer. So let's continue. So we had the equation of the polymer model, the Rouse. From this, we could estimate what is the Holstein-Uhlenbeck process. From this, we can calculate, so the mean is going to be 0. This is classical Holstein-Uhlenbeck. And then from this, we can calculate the mean square displacement. Just this is mean square displacement for Holstein-Uhlenbeck process, which is very well known. So I'll start probably writing here. So what is the mean square displacement for a one-dimensional? And if it's three-dimensional, it's x, y, and z. So you just have to multiply by d, the dimension. Let's assume everything is isotropic. Okay, so sigma p of t, which is the mean square displacement for this Holstein-Uhlenbeck process, is kappa is Boltzmann constant temperature divided by kappa p, 1 minus exponential minus 2t tau p. So this is a mean square displacement. Let's call it for xp or for up. So this is really up t. Let's say times 0. This is 0 squared. No, there's too many squares. Equals. Okay, so let me do it in dimension 1. If you're dimension 3, you have 3 times, assuming that everything is isotropic. And then kappa p is what is written here. And for sigma, this is for p different from 0. And if p equals 0, this is just Brownian motion. So this is sigma t. It's just, this is the motion of the center of mass. So you don't care about the polymer because you look at the motion of everything together, which is like Brownian motion, except that the diffusion coefficient, when you have n beads connected, is going to be d divided by n. So d center of mass, t, and d center of mass should be written somewhere. It's d divided by n. And I need to explain what is tau p. This is 1 divided by d kappa p. So I will write now either kappa p for what you have when you have beta, or when you have 2. Let's think beta equals 2. It's this case. So now let's go back. We can write the expression of rc square at time t for the mean square displacement. So let's take this guy, square it, take the average of a realization. Alpha Cp, this is a matrix which is independent of any time. Up is a solution of Holstein-Uhlenbeck, and we just calculated here the mean square displacement. And since all up here are independent, because obviously, you have one here, it doesn't depend on the other one. So they're all independent. So now when you average and you have the 2 of them, they're going to be equal to 0. So it's equal d. D is the dimension. For example, d equals 3, dimension 3. So this is u0 squared plus the sum, d times, the sum of 1 n minus 1, alpha pc squared multiplied by up squared average. And now we just replace everything here. So this is 2d c center of mass time t. This is just the motion of the center of mass. And now we have to write plus, this is better like this, d. So let's replace by kappa p, kappa Boltzmann constant temperature divided by nothing, because the sum, the kappa p is going to be inside the sum. Kappa p and then 1 minus exponential minus 2t divided by tau p. All right, from p equals 1 to n minus 1. Is this correct? Yeah, and now we are missing here this alpha pc squared in the sum. So the sum, there is a sum in alpha p, in kappa p, there's tau p. Tau p is defined here, kappa p is defined there, and alpha pn is defined over there. All right, so now let's just look. So now we are exactly interested in how this term behaves. So basically, if the time is very, very short, extremely short, I mean, there are 3 regions. What are those 3 regions? Now, just let's look at this.
I'm a little lost. What's the physical interpretation of R?
It's a point on one of these points. Any of the. I'll take now a point in the middle. I look. I calculate from this point, according to this, the mean square displacement. Okay. At this point, at this moment, we just follow these calculations, mean square displacement of this point, and now we are going to look at what can happen if there are 3 cases. If the time is very, very short, extremely short, time is about 0. Basically, what you're looking at is the position of a bead that hasn't, the time of the interference with the neighboring is not reached. So this is just really a diffusion. We are going to extract information about diffusion of the bead you are looking at. This is one time scale. The second time scale, suppose you wait very long time. Everything has a time to move, and what you are really looking at is the motion of the average motion of the bead, which is really like the motion of the center of mass. In between, this is where we have this anomalous regime, and this is what we would like to calculate, how to express this sum here in this intermediate regime, where you have a time t in between those time characteristic tau p, and tau p are related to kappa p according to this formula, and kappa p is in here. This is called those are the different time scales involved in this relaxation of the polymer.
Okay.
All right, so let's say 1, this is diffusion regime, time very short. Diffusion, so now let's be precise. Time very short, so it should be less than time n minus 1. So this is the diffusion, and we have basically RC squared, which behave like dt. Now, if the time, so this extreme t bigger than tau 1, and basically RC behave like 2d, d is the dimension, d is the center of mass, time t, where dcm is d divided by the number of beads. And in between, so this is not the anomalous regime that we would like to discuss. So when you are in between those times, and so for this, what we need is to look at this sum. So let's rewrite, so let's call it, I call this, or just, okay, everything, let's call it Sn. This is the sum here. So now we are interested in estimating Sn when we are in the time scale between tau 1 and tau n minus 1, which are the extreme part, I mean the extreme time scales. So this is d divided by kn. So k is now just the parameter sum of cosine squared 2c minus 1 multiplied by p pi divided by 2n 1 minus exponential should be minus 2t tau p, and then we have to divide sum for p equals 1 to n minus 1, and now we have to sine to the power beta p pi divided by 2n. All right, so now think about this sum as an integral, where you are going to see that p and time now are going to be mixed together. And so how do you do this? We can use how to replace this by an integral in a correct manner, I mean in approximation manner. We are going to use the Euler-Maclaurin formula. So let me remind you what it is. So if we have a function, if we have the sum of a function, a regular function, f of p from p equal 1 to n minus 1, this can be written as the integral from 1 to n minus 1 of f when n is large, sufficiently large, f of x dx, plus there is a residual term, f of 1, f of n minus 1. This is found, was found by Euler and other people some time ago, 112 f prime of n. So this is why we need some regularity. You have different derivatives, minus f prime of 1. This is for n true for any function, so let's use this for that function. Let's plug everything in here. And so let me concentrate for this calculation on the integral part. Of course, we need to calculate the other term to see how they contribute, but just to give you how it works, let's focus on how we calculate this. So this can be, we can split it in two integrals, the integral where you have 1 and the integral where you have the exponential. So this is going to be a sum of two terms, I1 plus I2, where I1 is going to be minus integration from 1 to n minus 1 of cosine squared 2c minus 1 p pi divided by 2n divided by sine of beta p pi divided by 2n, and then I'll take the one with the exponential. So this is why they have the minus tau p. Right, and there is the second term, is the guy where we don't have the exponential. This is a term with, so okay, let me write it. I2 is integration from 1 to n minus 1, basically the same thing. And this is very important here. This is dp. Integrate with this p variable. And now this is the same, cosine squared divided by sine beta, p pi divided by 2n, cos squared 2c minus 1, p pi divided by 2n, dp. Right, so this minus this is the f here that corresponds to that term. If n is very large, then for example, where is the expression? Yeah, so p is fixed. Let's suppose p is fixed, and let's go to the approximation of sine x by x. So we can approximate this by x. The first term here, when n is very large, c is fixed, we are going to make the approximation that it is 1. So I'll make some approximation, not necessarily all justified here, but let's do this. When you do then all this, you can check by looking at the error that what I'm saying is correct. I'll just give you the leading order term. So leading order term, so let's write this. minus t divided by tau p. So let's go slowly. Tau p is there. So this is divided by, so if I divide, I multiply by d, and kappa p. And kappa p is 4 kappa multiplied by sine. So squared, let's write it p squared pi squared divided by n squared. Is it correct? No, 4. Yeah, should be correct. So this is like 1, and now we have to divide by pi p, so p pi divided by 2n to power beta. And then we have to integrate this from 1 to n minus 1, plus some residual term, and we have to integrate dp. Okay, so now n is very large. We're going to use a change of variable here, and this can be written as the gamma function. So let's go slowly about this calculation. All right, I'll go to the board here. So let's do a change of variable. So in the exponential term, we get, so let's write u equals p to power beta, t divided by tau 1, and tau 1 is 4 kappa d, 4 kappa, yeah, pi divided by 2n to the power beta. Should not be beta here, should be 2. Okay, so now this is exactly the term here. So this term, I1, is going to be dp, so let's write it du, so we'll have to change variable. So we have exponential minus u, this is now u, and we have to replace this term here. And so when we do the calculation, you get u to the power 1 divided by beta minus 2, exponential minus u du. You have t divided by tau 1, n minus 1 here to power beta, t divided by tau 1. And there is a term here which is t to some power 1 minus 1 divided by beta. And then there are other terms. So this is minus 1 divided by beta, 2n to the power beta, pi to the power beta, and there is also tau 1 to the power 1 minus 1 divided by beta. I skip some steps, but basically you just write this as u. You express p as a function of u. So if you have something to the power beta, basically the p that is going to be here is going to be, so like p squared something is equal to u. So p is like u to some power, p some power u 1/2, and then you have a beta here, and then because of the dp you have another term here. That's why you have this term coming from here. You have the minus 2 coming, and so now you have to study this integral. And so we have to look at what happened in the different regimes. In this regime, this tau 1 goes to 0 because n is very large. So this limit is 0 when n goes to infinity because you have 1 over n. This goes to infinity because this is compensated by n to the power beta. This is where you start to get some constraint on beta. N to the power beta divided by tau 1. This has to go to infinity. And this is going to be represented like a gamma function. And then you get here the exponent t to the power 1 minus 1 divided by beta. This is how you get it. And then there is a constant here that, of course, asymptotically depends on some quantities. So you end up having something of the form 1 divided by beta, 2n to the power beta, divided by pi, t to some power tau 1, everything to power 1 minus 1 divided by beta, gamma of 1 over beta minus 1. So the minus here, and this is negative, so this multiplied by this is actually positive. And then what you get is you can estimate the first term. So this is this term here. Now you can estimate the term here. And then you can calculate all the terms. And you end up with a formula. Again, I'm not giving all the steps here. But the calculation is interesting because this is where the t to of this non-integer power comes in the calculation. So RCT or t plus 0 minus RCT0, you average this, make it squared, and this is of the order. So this is 2d center of mass t plus a constant t to some power 1 divided by beta. And then there are other terms that coming from the other element that I haven't calculated. It's 1 divided by minus t divided by tau 1 for t bigger than tau n minus 1 and less than tau 1. So basically the most important term is this one. The rest you can neglect. And you get this power here with the beta that is prescribed from the alpha, I mean from the exponent, so that if now this is equal to alpha, how we did it in the calculation, we found the alpha, we then use it to fix beta, and now you go to the construction that we've made, and now you can look at your simulations, simulate this, and then you can even extract and make sure that what you have is follow the theory. That there is no corruption due to all of the approximation that we did. You can get this exponent. Now what is interesting is where do you do this? Now you have data. How do you extract an exponent like this? This is a tricky question. Suppose I give you the data. So now, this is a remark. All right, we have some theory with some approximation and some leading order term. Now, if you look at what the data, what it says here, it says that there is some time scale that you do not control, and the time scale here, so it has to be not too small, not too large. But how do you how do you extract the information? Usually you end up with curve, this is the MSD, as a function of time. So if you have something perfect, you get a line here, and usually whatever is your process, you get, and then this is, let's say, confined Brownian motion. You go to here and say, right, I have to approximate the derivative at 0. But you cannot do that here. It has to be long enough. So how do you do? Well, it's not clear. It's not clear. I'll show you what. So we could find that there is an anomalous regime. So at the beginning, it has to be like diffusion. It's very, and back it has to be also very small. But it turned out that there is a regime, an intermediate regime here, where you go. So you go back here to some kind of tangent that has to be parallel to. I mean, has to be go to 0. So you have one like this and another like this. It's not very going to 0, but imagine that it was going to 0. So then we use function of the type t to some power alpha in some intermediate region Well, indeed, you could see that it was matching because we knew from simulations. But you could see deviation if you don't do it correctly. What is interesting is to have here a certain time window that is sufficient. I have no criteria to tell you where you should start looking at this, and at the point for a process that you don't know what is the time constant. Yeah.
If you rescale with t to the half or something, you'll get one plateau on the left-hand side and a different plateau on the right, and some transition regime in the middle, won't you?
Again, so you want to scale by t to some power, but what is alpha? We don't know alpha.
You know, the left-hand end is going to be a half, and then the right-hand end is going to be a half.
That's right.
So if you plot it against that, then you'll get a plateau.
Okay. So you're saying rescale your function f of t by t to 1/2 here, where you have something constant, and you're saying when you see the deviation, put your. It's a good idea.
Yeah. You'll see.
We haven't tried that. Yeah, probably this is something to try. Yeah, I have.
You're going to run into enormous trouble with this because the right-hand end is the statistically least controlled end.
You're saying by when you do this, because of the t here, you might have some large fluctuation when you divide by something very small.
Fluctuations at the right-hand end are gigantic, right?
That's right.
When you get one piece of information from each track. At the left-hand end, you get one piece of information from each step. So I'm not arguing with you, I'm just making a totally separate point, yeah.
Okay, go ahead. So you're saying that in here, so it's true that here you get this all fluctuations. In here, if you divide by 0, basically, when you do this, it's true that it can also lead to large fluctuation because you are close to the origin. This is what you had in mind?
I'm saying the left-hand end is going to be solid. You're going to be good at the left-hand end.
You mean here?
Yeah.
Yeah, I mean, if we...
The right-hand end is going to be problematic, and so finding the transition, you really, I think like you said, you want to look for the transition from the solid left-hand end to something different, right? Rather than looking from the right-hand end just for a transition there, because you're not going to have any idea about the right-hand end.
Okay.
I think that's what I'm trying to say.
So, what we thought about how to analyze this is to say, now, because we have some kind of uniform expansion, I mean, we know that it had to start at the beginning with t. Then in the intermediate regime we have this. Suppose now this is uniform, suppose. Why not, instead of just looking at the 3 pieces, just use a formula like this to match everything?
Just fits it.
That's right. Nobody has done this. I mean,
Reasonable thing to do.
yeah, this is not that old, you know, we published that maybe 1 year ago. This is something that, this is a type of idea that we had in mind. That go now with the asymptotics of, let's assume this is an asymptotics, and then it is valid uniformly, which might not be necessarily true, but at least now you have, let's say, a constant here, a constant there, you have 3 or 4 constants. You don't want too many to fit a curve, because then you can do just, but if you have some constraint, probably what you said, you know, about the beginning, that we can have in some region some good estimates, as Dan said, probably at the beginning of the diffusion coefficient. Probably in the end, we are going to have a lot of fluctuations. But if we have something uniform, that might be something to try. Look at this uniform. So just, I'm sorry, this is, I should have done something probably on the big screen, but this is what you have. So at the beginning, you don't know. I mean, red and green are the fit to t to some power. This is what Dan said at the end, where you get this fluctuation, it goes to the roof. And at the beginning, you see that there's some deviation because it has to have a different power law. So then there is a region here where you can use this t approximation, and we could extract from this compared to the simulations.
Can I ask some probably stupid question?
Go ahead.
So, tau 1 is just basically 1 over the spring constant, right?
Tau 1 should be, so this is, now you look at 4 kappa, so this is p squared, pi squared divided by 4n squared. For p equals 1, you get what it is. So this is pi squared divided by n squared.
Oh, so that's the smallest one. Yeah,
The
okay,
small-
sorry, yeah. So
yeah.
that's the softest mode.
Yeah.
It's the influence from far away, right?
This is the influence
Yeah.
of, yeah,
It's the long wavelength, right?
That's right,
It's far
that's right.
away, right? Okay. So, okay. And then your other one is
the one that then you start to have.
now n minus 1 is your neighbors.
That's right.
Is that right?
Yeah, tau n minus 1, because here you get this n minus 1. Now you get something where you see
Yeah, yeah.
this is the n
I'm just
and
trying
it
to figure out
goes
which way
away.
around they're going. Yeah.
Yeah.
Yes.
Okay, so yeah, this is basically where.
How do I estimate? So that means I should be able to estimate kappa, I guess, from this. Sort of effective kappa.
How do you want to? You mean by?
Or do you know kappa for however long your pieces are, and then you can estimate tau 1? Because how am I going to know my experiment is giving me the? I mean, what frequency do I set the camera in the experiment? Right.
Well, okay. Here there are interesting points. So to come back to your point about what is the model of your polymer, what should be kappa? Kappa has to do with some mean properties that you define, that you decide. It's related to b, the mean square distance. So at this stage, it was very hard to get information about this time scale. We don't know, I don't know how to do it. And we focused mostly on this anomalous exponent for, because this is what people are interested in. Now you are saying, let's be more precise and define your polymer model according to some data that will fix, for example, kappa. Then you can get some idea of your time constant, which is the time constant that you will get over there, the extreme left and right, where you have diffusion and diffusion. This is what you are saying. Get information from your model, from data, and be then more accurate in how you fit. What I can say is this.
Now, what I'm concerned about is you do your experiment and you fit it, and really, because you're sampling very, very slowly, compared to how fast you should be sampling, really you're picking up something completely different than what you think you're picking up.
What do you mean? What do you have in mind?
I don't know.
Here, you should pick up at the time scale the anomalous exponent of your system. This is, what here would you expect to get? What?
So the anomalous exponent is not due to the polymer; it's due to the environment.
How would you have? How do you make such a statement based on what? That's the alpha. What the environment would do in order to influence the anomalous exponent?
I don't know. I'm sure we can think of something, but you can always find a reason for anomalous behavior. But if you can't sample at the appropriate, there's a time scale here on that graph that you drew, right? And that time scale, I think, is basically set by the stiffness of the bonds, and possibly the number.
The coarse graining. It's bounds. Doesn't the meaning is what is the meaning here in terms of base pair? We have to be big enough. So what, for example, we did in some analysis is to change the sampling time to 300 to 80 milliseconds, and ask them, what do you observe? What should be? Is there some significant changes? And there were. So we found, for example, alpha was different, which is not clear. It should be independent. Obviously, this has to do with the problem of how you get alpha, how you estimate alpha. Again, this is new stuff, so it has to be tried and tried and tried to see how you refine. But I think in general, once you have your polymer model, you define a scale. Once you define a scale, using the correlation function, actually, you can get information about the relaxation time, which has to do with this. So we use also this to get some estimate about this time scale. You use the correlation function as a function of time and see how it decays. Okay, I think let's finish with the remark. This is a remark how you connect to data. In the last 10 minutes, let me start the mean first looping time, how you calculate looping. So this is, I can give the references. This is Amitai. So we wrote a couple of papers on this, but I think one is enough. And myself, this is phys rev E. There are physical review letter, but all the explanation is really in the phys rev E. This is in 2013. Asaf Amitai. where we explained all of the idea here. You do the simulation. How you do the simulation? You do the extraction and the simulation, not on data. And then we have a paper which is which is submitted, where we apply all of this to real data about double-strand DNA break. Now you have a break. You look at the break before. I mean the locus where you look at you have tagged your DNA before the break, after the break, and the locus is close to where you have induced the break. And so we can see differences before and differences after. And this is where we see the differences also at the scale at which you are sampling. It's not clear to us, I mean, what it means. Obviously, when you sample at a longer time scale, more of the long range time scale is coming, the modes, the different time scale in kappa p. If you wait sufficiently long enough, more of the polymer will contribute to your dynamics. This is the statement that we have so far. It's not quantified enough here.